this exact same thing. And so the first thing to learning this is we just got to flat out memorize it. We got to flat out memorize it, but then we have to take it a step further, understand it, and be able to apply it. So we just got to have this memorized to have a fighting chance for this stuff to make sense. Okay? So what's the input into sine? The input into sine is the angle swept counterclockwise from the 3 o'clock position on the circle. Okay? So it's an angle. It's swept counterclockwise starting at the 3 o'clock position. All those details are needed. Okay? What's the output? The sine. The vertical distance above the horizontal diameter measured in radius lengths. In radius lengths, or fraction of a radius. Radius length is a fraction of a radius. What's the unit circle coordinate?
Y coordinate.
The vertical distance above the horizontal diameter is the y coordinate. That's the y coordinate. Okay, cosine, what's the input? Exactly the same. It's the exact same angle. Swept counterclockwise from the 3 o'clock position. What's the output? Horizontal distance to the right of the vertical diameter. And what's the coordinate?
X coordinate.
The x coordinate. Okay, so this is the first half of your quiz and recitation. Not today, starting Wednesday. Wednesday, Friday, and Monday. After your holiday. This will be the first part of your quiz. We'll do it again. You got to have it, like I said, to make sense of it, to understand it. We first have to know it. We first have to know it. So, and all the details. Okay, so quickly, take 30 seconds. Estimate the sine, the values of sine and cosine for this picture. Go. Estimate the values and talk with the person next to you. So estimate the values of sine and cosine for the current location of the bug. Go.
Not this one. Almost. That's the angle. But which one? The answer is 1. I think it's around. I know it's less than 1, but y coordinate is less than 1. X coordinate is.
Okay, Nayara, what do you think about the sine? Can you estimate the sine in this picture? 1? She wants 1. Hayden, where's Hayden? What do you think? She wants, for the sine, she's estimating it's 1. What do you think? 1/2. Okay, we got 1 and we got 1/2. Where is Kyle Johnson? We got 1 and 1/2 for the sine. Agree with one of those or something new? For the sine, for this particular angle, input angle right here. 1/2. Okay, it's neither 1 nor 1/2. What is the, so is the sine? Is the sine is which coordinate? Okay, the sine is the y coordinate. So is it this right here, A, or this right here, B? A, it's the y coordinate. It's the vertical distance above the horizontal diameter. Okay, so it's not 1 or 1/2. What's a better estimate for that fraction of a radius, right? Go ahead. What's that? No, so you just memorized something from the past. We're estimating it based on, how could you know it's 0.866? See, there's every number from 1 to 0. That's not the only, there's not just 3 values of sine. There's every single number from 0 to 1 when you take the sine. Okay? Every single number is possible as this bug is in different locations. So you couldn't possibly estimate 0.866. You see, there's an infinite number of values from 0 to 1. So if we're just doing a loose estimate, what would it be? It doesn't seem like we're getting it. This is about 0.8, 0.85 maybe. Okay? Doesn't make sense. I'm not feeling like we're getting this. The vertical, if it's a vertical distance in radius lengths, what's the vertical distance in radius lengths at the top of the circle?
1.
1. So any other value in this quadrant is going to be how related to 1? A fraction of 1, right? So we're looking at this value, saying what fraction of 1 is that? That's what the sine is, the vertical height. What fraction of 1 is this? This is about 0.8. Okay, now, other one. So the cosine then obviously is our x-coordinate. So estimate the cosine, the horizontal distance to the right, or the x-coordinate. Let's see if we can do better on this one. Morgan, can you estimate the cosine? She says negative 0.5. Is it negative, first of all? Yep, it's to the left. How about her estimate of 0.5? Pretty good, okay? Maybe a little more. So 0.5 would be reasonable, but it looks like maybe a little bit more than halfway. So maybe 0.55 or 0.6. But 0.5 is totally reasonable. Okay, doesn't make sense. So these values of sine and cosine really end up being what fraction of the radius are we, either above the horizontal diameter or to the right of the vertical diameter. Okay? All right, so, but can we apply it? All right, so I got my runner here. He runs about half as fast as Usain Bolt. Okay? Takes him about 20 seconds to run 100 meters. And so you can see the application here. He's running around the track, starting at the starting position, which is like the 3 o'clock position. Okay? So I want you to work through this. I'll try to make that a little bigger. And I'm going to take attendance. But so now this is applying what we just talked about. When you go through these questions, you're not using your calculator, just your answers are going to be expressions. So no calculations, no calculator. Your answers are expressions like pi plus 3 or square root of 3 times 8 instead of getting an approximation. You're coming up with expressions for your answers. Okay, I'll make this bigger. Can you read that in the back? Is it big enough to read in the back? Cool. All right. So go slow. This arguably is the most important thing in the whole module, okay, is getting this. Really understanding sine and cosine. Okay, and angle. Okay, so go through slowly, work together. We really want to make sure we understand this and can do this. Okay? And I'm going to take attendance. All right, so I'm going to show you. The first question is about 22 meters. Here's the 22 meters, the question number 1. Here's its location, okay? Radians, how do we do on this? So we've got, he's run 22 meters. I'm showing him having run 22 meters on the track of radius 31.83. What's the angle in radians? Yusuf, did you get it? Didn't get the angle, okay? Jack?
It looks close to 5 quarters, but it's probably more close to 22 over 31.23.
Yeah, that's what it is exactly, right? Yeah, he's not quite to pi over 4. So to get this angle, what'd you say?
It's whatever 22 over 31.83
Right, and that's a perfectly fine way to express it. So 22 over 31.83. Because radians is the same as what? Radians is the same as?
Well, just a fraction of a radius length.
A number of radius lengths that he's run, right? So the number of radius lengths that he's run is the same as that openness in radians. We worked on that. We worked hard on that. Okay, so now I want to express his vertical distance above the horizontal diameter in radius lengths. Do that. Yeah, as soon as you see vertical distance above horizontal diameter, you immediately think that that's what? That's the sine. And what's the input into sine? The angle measure, right? And that's what we just found. So we've got our input, and to get the vertical distance, the sine, we need the output of sine when the input is that angle. Okay, so that's the answer to B1. Now if we want that vertical distance in meters, how could we get the vertical? Yeah, Evan. Yeah, right. So we know this is a fraction of the radius, right? That's in radius lengths. It's the fraction of the radius he is above. And so if we want to get how many meters he is above, we just take that fraction of 31.83. Okay, so angle is the input. If we just take the sine, we get that vertical distance in radius lengths. If we multiply it by the length of the radius, then we get it in meters. Okay, so now, cosine. Riley, you're up. Express the horizontal distance to the right of the vertical diameter in radius lengths. So C1 here, the horizontal distance to the right of the vertical diameter in radius lengths. How would you do that? Cosine? Good. Cosine of that same angle. Okay? And then keep going. Now how would we get that horizontal distance in meters? Yep. So the ideas here and being able to represent these quantities, like I said, this is arguably the most important thing in all of the module, okay? Because this is really understanding what sine and cosine are. Okay, so now we want the coordinates. If we want the coordinates of his position in radius lengths, what would the x and y coordinates in radius lengths be? Joseph, I want the x and y coordinates of his position right now in radius lengths.
X is 0.77 and Y is 0.63.
How'd you get the 0.77?
I did cosine data.
Cosine of our angle. So this much of it would be our x coordinate in radius lengths. And what'd you get for the y coordinate?
0.63.
Okay, so one way to represent his coordinates is 0.77 and 0. I'm going to do 64. Okay, why do those numbers make sense? How can we make sense out of that? Given his position, what you see there, how can you make sense of those numbers, 0.77 and 0.64? Taz, what do you think? Yeah, so why do these, if you look at this picture right here, why do these numbers make sense? How do those numbers?
Because sine is the horizontal distance and the vertical
Okay,
axis, and then the vertical axis is cosine is from horizontal, like one. So it's like
so this is cosine here?
um,
Distance from the horizontal, that's what you said.
That's sine.
sine is, I mean, like sine is with y.
Okay.
And then cosine is in x because it's distance from the right side or the right side.
So what's this value right here? 0.64, okay. And so how does that make sense, that that's 0.64? Travis.
It's closer to the midpoint between 1 and 0.
Okay.
But it's closer to 1 than 0.
Good, yeah. So he's saying it's pretty close to the midpoint, which would be a half, but it's higher up. It's higher up than the midpoint, or a little bit further than halfway up. 0.64. 0.77, same thing. 0.77 is, it's about 3/4 of the way.
It's a little bit more than that.
Little more than 3/4 of the way from 0 to 1 in terms of the x-coordinate. Okay, so now what about in meters? Did you get estimates in meters? Somebody knew. So how do we get meters? What did you get? Abdulaziz, did you get meters for these coordinates? So we got it in radius lengths. That's 0.77 radius lengths. How would we get that distance now in meters? That horizontal distance from the vertical diameter. Okay. Yeah. Take that and multiply by 30. Did you do that? Do you know what that is? Who's got it? Mitchell, you got it?
Yeah, it's 24.51.
24.5. Okay, so these numbers should make sense in terms, if the radius is 31, he's 24.5 feet out to the right of the center, and he's about 20 feet up from this horizontal diameter. Okay. Really, does this make sense? Anybody have a question? Okay, so if you haven't yet, so let's repeat it for 59 meters. And instead of showing the picture, let's do the math for 59 meters, and then guess where he would be. Okay, so based on the results you get from the math, guess where he would be on the track, and then I'll show. And then after you're done, I'll show you. Okay, so work it out for 59 meters now. So now he's run 59 meters. Same thing, same process. If you haven't already. Question? You might be in degrees. Calculator. Mode. Setup. Switch it. Oh, Bayesian's forward there. So is it done? No, I'll try. See if it works now. That's better, but although it looks like you got run over. Tire tracks. Okay, Colin. How about his coordinates in radius lengths if he ran 59 meters? In radius lengths. So, and what is theta? Cosine of what? 22 over 59. What do we think?
Oh, yeah.
So the angle, what is the meaning of the angle? It's how many radius lengths he's run. So how many radius lengths he's run? There you go. So you're going to take the total arc length, divide it by the radius. It gives you how many radius lengths he's run, and that's the same as our openness in radians. Okay, anybody got these values? 59 or?
That's negative 0.28,
Okay,
0.96.
okay. So now, based on that, can you imagine where he is at this moment? So let's try again. So cosine of 59. So from those numbers, I heard negative 0.22, 28, and 0.96.
Yeah.
Okay, so now based on those values, you should have an image of where he ended up. You should have an image based on those coordinates, negative 0.28, 0.96. Can you predict where he would be if he runs 59 meters? So, tell me where to stop. Yeah, right around here. He's going to go just about a quarter to the left, and it'll be almost all the way one radius length up. So if I set this on 59, there it is. So this is him running 59 meters. He's a little more than a quarter to the left of the vertical diameter, and almost all the way, 96% of the way up to one full radius length. And so then in meters,
Negative 8.6. 30.6.
numbers should make sense, knowing that our radius is 31.83. That should make sense. He's about negative 9 meters to the left, and almost 31 meters up, 30.6 meters. Okay, any questions on this really important activity? Questions on all the meanings here? Okay? Like I said, could be, if we want to do one thing in this whole module, we would want to learn this, because this is what sine and cosine are about. But there's lots more to learn. Okay, so let's talk about, we said every circle can be thought of as the unit circle. And so in any circle, how can we think of what the meaning of 1? Right? In any circle, we can make that radius 1, and then the meaning of that would be 1 radius length, right? 1 radius length. So any circle in the universe can be the unit circle, and that 1 stands for 1 radius length. Okay? And so how did we get our radian? Why did that do that? Okay, how do we get our radian measure? We started with the radius, right? And we took that radius and we pulled it off its normal spot and we wrapped it on the circle. And we said that openness of the rays that cut off 1 radius length was what? What angle is that?
1 radian?
1 radian, right? The openness in radians is the angles whose rays cut off 1 radius length. Okay, and so we could keep wrapping radius lengths around the circle. Wow. And here's where we end up. 1, 2, 3, 4, 5, 6. Okay? So it's good to know that and understand where those spots are, because they're the whole number of radius lengths. But the disadvantage is they're not in nice places on the circle. Okay? They're not in nice places on the circle. So we talked about what halfway around the circle is, right? What's halfway around the circle? A little bit more than 3, and it's exactly pi. And from that now, we can make all these nice symmetric places on the circle. For instance, top of the circle.
Pi over 2.
Put pi over 2 in your calculator. What number do you get? A little bit more. So why does that number make sense? Based on what we're looking at. Yeah, so this was 1 radius length, and this is 2, and this is, see right there at the top, is a little bit more than 1.5 radius lengths. So when we have all these values with pi, don't forget that those values are still how many radius lengths we're going around the circle. Okay, bottom of the circle. Right, so it's 1.5 pi. 3 pi over 2. And then all the way around is 2 pi. Okay, so those are our first 4 angles that we've got. 0, pi over 2, pi, 3 pi over 2, 2 pi. And so what we can do then is we can cut those in half again. So we cut those in half again. So what do we get right here? Pi over 4. Now here's how I want it. So we're going to have to memorize all these key angles. We call them the key angles. Okay, we're going to memorize them all. But here's a way that helps you. So this is when you cut them in half. Now these are by pi over 4. So all you have to do is count. 1, 2, 3, 4. So this is 1 pi over 4. And so then when we get to the top of the circle, that's 2 pi over 4. So does it agree with that? 2 pi over 4. 3 pi over 4. 4 pi over 4. Does it agree? All you got to know is know how to count. 5 pi over 4. 6 pi over 4. Does it agree? 7 pi over 4. And then 8 pi over 4. Does it agree? 8 pi over 4 is 2 pi. Okay? So you just, for pi over 4, you just count 1, 2, 3, 4, 5, 6, 7, 8. That can help you remember these angles that are the pi over 4 angles. Okay, similarly, so now we can take pi and we can break the first half circle up into 3 parts. Okay, into thirds. But they're not showing up. Why aren't they showing up? Okay, anyway, so we'll go right to sixths, all right, and the thirds will come out of the sixths. So the blue ones now are the sixth, a sixth of pi. And we're going to do the same thing. We're going to count. So the first one here is pi over 6. This is taking the half circle, divided in exactly 6 pieces. And so now we're going to go around the circle, and we're just going to count. 1, 2, 3, 4. And then whenever we can reduce a fraction, we will. Okay? So pi over 6, so that's 1 pi over 6. Then 2 pi over 6, which is
Pi over 3.
can be pi over 3. 3 pi over 6. Does it agree? 3 pi over 6.
Yes.
4 pi over 6, which is
Pi over 3.
2 pi over 3. Again, 1, 2, 3, 4 pi over 6, 5 pi over 6, 6 pi over 6, obviously is pi, 7 pi over 6, 8 pi over 6. That one we can reduce.
4 pi over 3.
4 pi over 3. 9 pi over 6. Does it make sense?
Yes.
10 pi over 6.
5 pi over 3.
9, 10, 11. And then 12 pi over 6 should be 2 pi. Is 12 pi over 6 equal to 2 pi? Yep. Okay, so that's one way to help you memorize these key angles. Okay, I gave Chandler a hard time earlier. So these are the key angles, but they're only 16 of how many angles all the way around the circle?
Infinite.
There's an infinite number of angles, but these are in nice symmetric places, right? We divided pi up into 4 pieces, and then we divided pi up into 6 pieces, so that they end up with symmetry. But it sometimes what happens is then you think that these are the only angles on the circle, right? There's from 0 to pi over 2. How many angles are there?
Infinite.
Infinite number of angles, right? There's an infinite number of angles from 0 to pi over 2. Okay? So now, what about the sines and cosines of all of these? The sines and cosines. So we'll start with the pi. So we should know these, pi over 2, pi, 3 pi over 2, and 2 pi. All right? For instance, what's the cosine of pi? What's the cosine of pi? What's that? -1. Why? Because the cosine is the x-coordinate, or the horizontal distance, and at pi, we're -1 to the right of the vertical diameter. Okay? What is the sine of pi over 2?
0.
Okay, I heard 1 and 0. What's the sine of pi over 2?
1.
So you got to think sine is which, what is it, vertical or horizontal? Vertical, so it's +1. What's the cosine of 3 pi over 2?
Horizontal, 0.
Horizontal, cosine's horizontal, so at 3, here, we're at 0. Does it make sense?
Yes.
Okay, so then we look at the ones we cut all these in half here. And so the question is, if we go halfway up to the top, what is the sine and cosine, say at pi over 4? So here's the quick and incorrect answer that students often give. Oh, well, it's 1/2, right? Because if you go halfway up the circle, you're going to be halfway to the right and halfway up. We clearly see that's not right. What is it about?
0.7.
Yeah, so we're close to 0.7 here. You see? And up here, 0.7. So there's symmetry to it. They're the same, but they're not 1/2. Why? Because the circle arcs out, right? It's not a straight line from here to here. The circle arcs out, so it kind of stays further away. The circle, and so when we get halfway up to pi over 4, we're something around 0.7. So let's get that exactly. How can we get that exactly? So what we can do is we can draw a triangle. What's that length right there, from there to there? That's 1. That's our radius. Okay? And what's this right here? How can we say what that is? We're estimating it's 0.7, but what is it exactly? That value right there, that length. Cosine of what?
1. No, wait. Pi over 4.
Pi over 4. It's the x-coordinate when the angle's pi over 4. And then up here,
Sine of pi over 4.
sine of pi over 4. It's the y-coordinate. But because of the symmetry of this, those are the same. You see? Those are the same because we are at pi over 4. We're halfway up to the top. So by symmetry, those are equal. So let's call them A. How are we going to solve for A? So we got A here this way, A this way, and a hypotenuse of 1. How can we solve for A? Pythagorean theorem. So what would it be? A squared plus another A squared equals 1. Make sense?
2a squared.
What's that?
So it's 2a squared.
2A squared equals 1. And so A squared equals
1/2.
1/2. And so A equals,
Square root of 1/2.
and if you put that in your calculator, square root of 1/2, you get, oh yeah, so it's square root of 2 over 2. Yeah, I should have done 1/2 there. Okay, square root of 2 over 2 is approximately equal to, and that's what we saw, right? We estimated it's about 7/10 of the way to 1 full radius. Okay, and so now we didn't just learn a sine and cosine for 1 point, we actually learned a sine and cosine for 4 points. Because by symmetry, the square that I've drawn, so what is the cosine of 3 pi over 4? The cosine of 3 pi over 4? It's going to be, so it's going to be now negative because we're to the left, but it's going to be the same value. So the cosine of 3 pi over 4 is negative radical 2 over 2. All right? What's the sine of 7 pi over 4? Negative radical 2 over 2. So they all have magnitude. All these coordinates have the same magnitude of radical 2 over 2. All you got to do is decide if it's positive or negative based on is it above, below, left, or right. Okay, so now let's look at we'll look at pi over 6. So let's just estimate first. So this is our pi over 6 angle. All right, and what it turns out to be is at pi over 6, that vertical distance above turns out to be exactly 1/2, and I'm telling you that and show you, but it turns out that that's exactly 1/2. Okay, and the radius is 1. So we could solve for, is this cosine or sine? Cosine or sine, that length right there? No, it's horizontal distance in the x-coordinate. Cosine. So we got a squared plus 1/2 squared equals 1 squared. And when we solve for a this time, we get radical 3 over 2. So the coordinates of this point are square root of 3 over 2, 1/2. Coordinates of this point are and when we get up to pi over 3, it's symmetric with this, but they're flipped. Now the x-coordinate's 1/2, and the y-coordinate is the same as what we solved over here. Okay, so by symmetry then, if you know these cosines and sines are x and y coordinates for the first quadrant, then you know them for all just by applying the right either positive or negative. Okay, and so that's your second part of your quiz. In your recitation, let me show you. You're going to get a sheet of paper that looks exactly like this. And I'm even going to post it on Blackboard so you can practice as many times as you want. And you're going to get this sheet of paper and you're going to fill in all the radian measures, all the degree measures for the 16 key angles, and all the sines and cosines, or x and y coordinates. And so that will be starting next Wednesday. And you'll have homework due Wednesday and lecture as well. I won't see you Monday. Wednesday is the first one. Wednesday, Friday, Monday.
When you post this, can you post it with like the actual numbers on it?
No, you should practice figuring it out. But you can find it all over the internet.
Okay, yeah.
Yeah.
Easy.
Well,